All right, so we just finished going through some basic exponent laws, working on equations. Now we're going to work on word problems. So if you deposit $2,000 in the bank, $2,000 is important information. I'm going to circle my important information at 12% interest. How much will you have after 8 years? So on your formula sheet, we're going to start off with future equals present, 1 plus the interest rate to the exponent time. If you'd like to work through theory, please feel free to check out the notes on the theory. So the future value we don't know. The present value in the equation is 2,000. 1 plus the interest rate, 0.08 to the exponent time, 12 years. So this we can type in directly into our calculator and get $4,951.93. Circling our answer, a logic check, always logic. If I put $2,000 in the bank, 10% will be about $200. Now if I do that for 8 years, it's going to be about $1,600. So if I take the present value of 2,000 plus the approximate 1,600, I get 3,600. Now what is with the difference between 4,900 approximately and 3,600? Well, we're going to be making interest on interest. So as the $200 of interest accumulates each year, the following year we're then going to make interest on that interest. So $4,951.93 is a good logical answer and correct. Okay, find the rate to triple your money in 10 years. So we're working with money. We're usually going to start off with future equals present, 1 plus r to the exponent t. Now we're finding the rate to triple. So what would our present value be and what would our future value be? Well, it's arbitrary. I'm going to call my present value 1, and therefore if I triple it, a future value of 3. Notice we didn't get that information in the question, and we could have just as easily arbitrarily started off with a different present value. So 3 equals 1, 1 plus r to the t. Excuse me, t is 10 years. So now I can simply divide by 1 and that goes away. So I have the equation 3 equals 1 plus r to the exponent 10. Now we learned in 7.1 and 7.2 that if we want to solve for a variable with an exponent, we take both sides to the reciprocal exponent. So the reciprocal of 10 is 1 over 10. So we're going to take both sides to the reciprocal exponent. So on the right-hand side, if I do 10 times 1 over 10, well, that just equals 1. So the exponents go away, and that was the goal. So I have 3 to the 1 over 10 is equal to 1 plus r. Now I can simply subtract 1 from both sides and mirror the equation, and I get 3 to the 1/10 minus 1, which works out to be 0.1116, and if I times that by 100, I get 11.16%. If you'd like to try logically, feel free to create a model to see if you triple an amount by 11% each month, following the formula. Each year, 100 times 1 plus the decimal, 0.1116, and take it to the exponent of 10. And we should get approximately 3. Tripling what we started with. Excuse me, 300. Tripling what we started with. Feel free to see the notes and feel free to check your answer on your own. Okay, if you deposit $5,000 in the bank at 8% interest, compounded quarterly, how much will you have after 6 years? So if we're compounding, we're going to use a very similar formula, a little different. It starts off the same, F equals P, open bracket, 1 plus, but this time we're going to take R and divide it by N and take it to the exponent Tn. Now, if we're compounding yearly, these n's go away and we're left with the same formula that we had before. F equals P, open bracket, 1 plus R to the exponent T. Now, we are not doing that right now. So, we're looking for a future value. We have a present value of 5,000. 1 plus the interest rate, 8%, 0.08, over. Now, n is the number of times we compound per year. So if we're compounding quarterly, that's 4 times per year. Not 3 for 3 months, but 4 for 4 times per year every 3 months. To the exponent, t is going to be 6 years, times 4n, the number of times we compound per year, quarterly, and we can simply type this into the graphing calculator and get $8,042.19. Again, feel free to logic check. This answer is correct. Please feel free to check out the notes. Feel free to try out a question on your own. Make up a similar example. Substitute all the information. Do a logic check. So, if a population starts at 1,000 and triples every 4 hours, how large will the population grow in 25 hours? So we're going to use the same formula as the banana equation we worked through in the section before. So future value is present value times the rate to the exponent lowercase t over capital T. So we'll talk about those slowly. So we're wondering how large. That is a future value we don't know. Our population starts at 1,000. Now our rate. So our rate is tripling. So if we're tripling, our rate is 3. In the banana question, it was a half-life, so it was a half. If we're doubling, it's 2, tripling, it's 3, etc. Now, if we're going to be growing in 25 years, that's the time that has actually happened, lowercase t. Now, the time for the tripling to occur is capital T. Now that tripling occurs every 4 hours. That goes on the bottom of the fraction. Now I can simply type this into my calculator and I can get a population of 959,417 population. Now notice I didn't keep any decimals because that is a population. That is a real-life example whereby you have to state exact values as we have numbers of people. A little logic check. We have 1,000. We're tripling every 4 hours. So in 25 hours, how many triples that will be? Well, 24 goes into 25 about 6 times. So we're going to triple about 6 times. So we're going to start off with 1,000. Then if we triple, will be, after one tripling time, will be 3,000. Then if we triple again, will be 9,000. Then if we triple again, will be 27,000. Then if we triple again, will be 81,000. Then if we triple again, will be 240,000 or so. And then if we triple again for the sixth triple, approximately, will be about 750,000, which is incredibly close to our actual answer. I cannot stress enough how important a logic check is at the end, especially when you're unfamiliar with how these formulas work, or interest or growth altogether. Okay, if a population starts at 300 and grows continuously at a rate of 0.06, how large will it grow after 20 days? So if you ever see the word continuously on the formula sheet, we have a formula specifically for that. That formula is future equals present always. Now our base is e to the kt, where k is the rate, t is the time, and e is the exponential growth rate. Euler's number E is 2.71. E equals 2.71. And we'd have to do a lot more calculus to worry about that number, but outside of that, we're just going to go with it. So the future value, we don't know. We're looking for the future value. The present value is 300. E, the brackets were unnecessary. K is 0.06 times the time of 20 days. So there I can just type that into my calculator and I get 996. And again, that is a population, so we are going to round to the nearest integer. And it would be a lot more difficult to do a logic check on an exponential growth. We just want to think approximately. So 300 growing at 0.06 in 20 days. Well, if that's 0.06 per day, well then that's going to be about 6% a day, and then we could see that growth pattern. Feel free to try that on your own. Okay, how many times as intense is an earthquake of 6 then 3? So a little bit about earthquakes and Richter magnitude. If you have a earthquake of Richter 3, a 4 is 10 times as strong as a 3. And a 5 is 10 times as strong as a 4. So if a 4 is 10 times as strong as a 3 and a 5 is 10 times as strong as a 4, that means that a 5 is 10 times 10, 100 times stronger than a 3. So we are going to assume that we're going to get 1,000 times stronger. So we're going to use another formula on the formula sheet. The intensity of an earthquake is equal to 10 to the bigger earthquake minus smaller earthquake. Now this formula can be used for all sorts of types of questions like acidity in science. However, they should usually give you a table, as bigger and smaller may get a little bit confusing. So how many times is intense? Is a 6, the bigger earthquake, minus a 3, the smaller earthquake. Well, that's I equals 10 cubed, which the intensity is equal to 1,000 times as strong, as we predicted. If, for example, they gave you the intensity, we would substitute that in for I, and we might have to solve for one of the exponential variables, which we'll see later. Okay, find the present value of a worth 2,000 at 10% in 4 years. So we're back to money. So future value is present value times 1 plus the interest rate to the exponent time. So our future value this time is 2,000, substituting on the left-hand side of the equation. is equal to the present value we don't know, times 1 plus the interest rate, 10%, 0.1, to the exponent time 4. So if the left-hand side stays, I'm going to work this out. So 1 plus 0.1 is 1 plus 0.1 is 1.1, to the exponent 4 is 1.4641. So I'm going to clean that up. So 2,000 is equal to 1.4641 p. Now I'm simply going to divide both sides by that number, excuse me. And if I mirror the equation, p is equal to 1366.03. Back to keeping decimals when we're working with money. And a nice little logic check, at 10% for 4 years, 1,300 will grow to about 2,000. Okay, find the rate of a $1,000 deposit worth $1,100 after 2 years. So, again, we're working with money. Future value equals present times 1 plus the interest rate to the exponent time. So it's worth $1,100, so that's a future value. The present value was what we started as, 1,000. Now we're looking for the rate, so 1 plus r to the exponent t. Now t is 2. So I am going to divide both sides by 1,000. So 1.1 is equal to 1 plus r squared. Now, again, how do we solve this equation? Well, the notes from 7.1 and 7.2 tell us that if we have a variable, we want to take both sides to the reciprocal exponent. So the reciprocal of 2 is 1/2. So we take both sides to the 1/2. Now we do that because on the right-hand side, 2 times 1/2, the exponent is just equal to 1. So that eliminates the exponents. So we simply have 1.1 to the 1/2 equals 1 plus r. So if I subtract 1 from both sides and mirror the equation, we have 1.1 to the 1/2 minus 1, giving us a rate of 0.0488, or simply 4.9%. Great. Okay, how much time, excuse me, to quadruple your money? At 8%. So we're working with money, so let's start off with the money equation. P, present equals future equals present, 1 plus the interest rate to the exponent time. Now again, before we worked on if you triple, now if we quadruple, a present value of 1 and a future value of 4 if we quadruple. So my future value is 4. I have a present value of 1. Now my interest rate is 0.08. And t, we're looking for how much time. So I can divide both sides by 1 and I can clean it up. So this equation is a little bit more difficult. We cannot solve this equation algebraically. We don't have any methods yet until the next chapter when we work on logarithms. So when we work on those, we'll get there, but for now we want to apply the method where we make y1 equal to the left-hand side and y2 equal to the right-hand side. So on the graphing calculator, y1 equals 4 and y2 equals 1.08 to the t. So if we take out our graphing calculators and we graph that, y equals 4 and y equals 1.08 to the exponent x, and then we graph that, I'm just going to start with a nice, easy window to begin on, such as zoom 6 gives us a nice 10 by 10 window. So I know I'm working with money. I can't have negative money, technically. So it's going to be just a nice little L graph like the banana. And the first line that is drawn, I've just got a nice 10 by 10 window. The first line it drew was y equals 4. And the second line, it looks as though it's going to come up like this. Now I cannot see that intersection, so I need to make the window like 20 or 30 in the x direction. So get in the habit of playing around with your window and really seeing what works. Be careful with some of the calculators, they're a lot slower than others. I can see the intersection now. So second, calc, 5, enter, enter, enter. We'll find that intersection, and it has an x value of 18.01 and a y value obviously of 4. Now x is t in this equation, so t is equal to 18.01, and don't forget your units. It says how long. Now I didn't include any units, so t is just 18.01. Sometimes we're going to graph it that way. We can solve it with graphing. We could solve by guess and check. You could do 1.08 to the 7, 1.08 to the 9, 1.08 to the 15.2 and find out which one's closest to 4. We can also do performances like change of base sometimes. So we're going to have a multitude of different methods. Algebra, change of base, graphing calculator, guess and check, and eventually logarithms. And we need to be able to recognize when we can or have to use each different form. So if we deposit $100 in the bank, how long will it take to grow to $6,400 if it doubles every year? So I'm going to use the growth and decay formula. F equals P, open bracket, r to the lowercase t over capital T. And let's substitute. So the future value is going to be 6,400. Our present value is going to be 100. Our rate, so we're doubling, is going to be 2 for doubling. As we've seen in the past, tripling 3, quadrupling 4, half-life 1/2, 2 for doubling. Now, how long? We're looking for the exponent t. And capital T, the time for the rate to occur is just 1. So this is going to clean up nicely. Let's see what happens. So 6,400 equals 100 times 2 to the t. Now, before we continue solving that, let's see if sometimes we can use a different formula. So F equals P open bracket 1 plus R over N to the exponent Tn. Now, we are a future value of 6,400, the same, equals a present value of 100. Notice the same so far. Now, if we're doubling, well, what's our rate? Well, we want to be double what we were in the past. So if we start off at 100%, if we double, we'll be 200%, increasing a rate of 100% or 1.00. Now, this rate is happening each year, giving us our R of 1. T we're looking for. And again, if this happens each year, N will be 1. So let's see how this cleans up. 6,400 equals 100. 1 plus 1 is 2 to the t. Notice we have the same formula. If you're really good with these different formulas, you can go back and forth, but I would stick to the formula on the right for money and the formula on the left for growth. So let's continue. We're going to divide both sides by 100. Again, I'm not going to actually do it. I'm just going to say I'm going to do it. Now 6,400 divided by 100, I can cross off a 0 from the top and the bottom, and 64 is equal to 2 to the t. And this one, we're not going to use our calculator. 64 is simply 2 to the 6. And I have the same base, so I can make the exponents equal to each other. 6. Now I can do a logic check. If I have 100 and I double once, I'm 200, then 400, then 800, then 1600, then 3200, then 6400. The amount that we said we are going to get to in 6 doubling times. 6 years. Don't forget your units. So sometimes we're going to solve by formulas and just type it into our graphing calculator. Sometimes we're going to use a graph to help. Sometimes we're just going to do change of base. Sometimes we're just going to do guess and check on the number line. And next chapter we're going to work on logs. All of these methods that I speak about are on your methods sheet. Okay, an earthquake in California, Richter of 8.5 magnitude, 100 times as strong as a earthquake of what Richter magnitude? So we're going to start off with the intensity equation. I equals 10 to the b minus s. Now this time the intensity was 100 times as strong, equals 10 to the bigger one minus the smaller one. So was 100 times as strong. That means that 8.5 is the bigger one, 8.5, minus the smaller one that occurred. Now, I know that 100 is simply 10 squared. 8.5 minus s. And if I have the same base, I can make the exponents equal to each other. And I can solve for s. So if I add s to both sides and if I subtract 2 from both sides, I get s equals 6.5. And the units, Richter magnitude. The smaller earthquake was a 6.5 Richter magnitude. And if we remember, a 7.5 is 10 times as strong. Therefore, an 8.5 must be 10 times 10, 100 times as strong. Logic check always. All right, light diminishes by 10% every 5 meters. Find the depth at 1%. So we're going to use growth and decay. We'll get more and more familiar. Future equals present times the rate to the lowercase t over capital T. By doing more and more examples, you'll start to see when is a good time to do different or use different formulas. So light diminishes. Now so light diminishes by 10%. 10% will be the rate. Well, that will contribute to the rate. So that will contribute to R. Now, 5 meters, that is how long it takes for the rate to occur, or the amount. Now, find the depth of 1% of light. Well, I don't know my present value or my future value. So I'm going to arbitrarily start off with a present value of 100. Therefore, my future value is just 1% of that 100. So my future value is 1, my present value is 100. My rate, now what's my rate? So if I'm diminishing 10%, well, if I go down by 10%, well, that means that I'll want a rate of 90%, because my rate, the thing inside the brackets, is always the percentage that we want in the future. So my rate will be 0.90. To the exponent, we're looking for find the depth. So t, this time, the time that's going to be happened is the d, the amount, the depth. And this occurs every 5 meters. Now I'm going to start off by dividing both sides by 100. Therefore, 0.01 is equal to 1, open bracket, 0.90 to the d over 5. Keep in mind, I could have arbitrarily started off with a present value of 1 and a future value of 0.01 because that is a more simple way than we did previously. All of these methods are on your formula sheets for each chapter and the yearly formula sheets. So I can divide by 1, that's gone. Now I have this interesting looking formula. So how am I going to solve that? Let's simplify it a tiny little bit. So again, like we've seen before, we have an exponent in the variable in the exponent. So we have no way to solve this algebraically, and we have to use the graphing calculator. So again, we're going to do y1 equals the left-hand side, and y2 equals the right-hand side. And remember, we're putting x as the variable because we don't have a d variable on the calculator. So x 0.9 to the x over 5 and 0.01. So now before I even hit my window, I know I can't have negative percentages and I can't have negative time, so I'm going to draw an L graph. But I know that one of my y values is 0.01, so I'm going to go right in and change my window to go from a y minimum of 0 all the way up to a y maximum of maybe 1. Not even. 0.1. 0.1. And then I don't know how long this is going to take, but I usually have to make my x bigger. So I'm going to just make my x go from 0 to 20. And then if I press graph, I'm going to first see my y1, which is just a nice and simple horizontal line. But I can't see my other line because it has a y value of 0.9. So I'm going to go back in and change my y window to go up to be about 2. And again, we never really know. We just want to try and see and try stuff and keep going and figure stuff out. So, for example, if you can't see something, change your window appropriately. So what I have is the first graph and the second graph together. Now, what's happened is I can't quite see my lower line anymore. Because I've made the window this, it actually brings that line so infinitesimally close to the x-axis that you can't even see it. Now, just remember it's there. Now with this window, I still can't see it. So what I need to do is increase my window. And without bothering to do 20 and 30 and 40, I'm just going to go right in and make it 100. Making the window as big as you want to. Again, I can't see it. So I'm going to go back in because it looks like this and I can't see the intersection. So again, I'm going to go in and I'm just going to make the window like 500 and press graph. So making the x like 500. Now I can clearly see that this other graph goes down and does something close. Who knows what's happening there? But I remember my old line, so I'm just going to do second calc intersection 5, enter, enter, enter. And then I can find that intersection of 218.54, comma 0.01. Obviously, this is the y value because one of the equations says that exactly. Now remember, I was working with t, and then I was working with d, and now I'm working with x. So I have to remember that my d variable is the one I want. So d equals 218.54 meters because I was working with meters in the beginning. Much more complicated word problem. A lot went into that. Remembering that 10% is actually a rate of 0.9. And all of that stuff with the window, etc.